Hello, this is third lecture in this series of photochemistry. In earlier two lectures, we have been talking about the initial first one on the basic principle involved in photochemistry, and in the second lecture, we have discussed about the photochemistry of few representative organic molecules such as alkene. We have mentioned that alkene undergo cis trans isomerization both under direct photolysis as well as under indirect photolysis. And it is possible to convert more stable trans isomer to less stable cis isomer. We have also mentioned that there is always an equilibrium between cis and trans isomers during the product formation because hence it is not possible to uh, convert to achieve 100% conversion because of the stability of the trans isomer, and hence it is always in equilibrium cis trans isomerization. We have also mentioned that in the cis isomer, when we have a proper substituent in the cis orientation, such as cis is still bean, and it is possible to undergo these molecules may also undergo under photolytic condition 6 pi electron cyclization to give dihydrophenanthrin derivative. We have also mentioned a few examples of this. Today we are going to talk on photochemistry of dienes, especially 1,4-diene and 1,5-diene. These two dienes undergo interesting especially 1,4-diene undergo interesting photorearrangement in which we are going to take quite a few examples of these rearrangement, because these dienes from open chain it is possible to undergo di-pi-methane rearrangement to give the cyclopropane derivative and highly ring strain system, which is not easy to construct, but during this transformation it is possible to this. Next, this is the transparency explains how 1,4-diene. So this is the basic skeleton of 1,4-diene. We have a 1, 2, 3 and 4, 5 system. You have a 2 double bonds between carbon number 1 and 2, and the second double bond between 4 and 5. So 2 pi bonds separated by a methylene group. So this is the basic criteria for the reaction to undergo photorearrangement. When we have a system like this, under photolytic condition, one of the double bond gets excited to give you 1,2 diradical, and then it may undergo cyclization to give a 1,4 diradical via the formation of cyclopropane. So initially under photolytic condition goes to 1,2 diradical, then this diradical may react with double bond to give you 1,4 diradical, and then it can further undergo cleavage of the cyclopropane ring, not the newly formed bond but the old bond, to give a 1,3 diradical, and then cyclization of this 1,3 diradical to give you vinyl cyclopropane. So essentially in this rearrangement, 1,4-diene undergo rearrangement via under photolytic condition via 1,2 formation of 1,2 diradical, and then 1,4 diradical, and then 1,3 diradical, followed by cyclization to give you vinyl cyclopropane. This is a very interesting for a rearrangement, because from an open chain system we are going to construct a highly ring strained cyclopropane ring which has a lot of synthetically important, and this rearrangement is also known as di-pi-methane rearrangement, because whenever we have a 2 pi bond separated by a methylene group may undergo this type of rearrangement to give di-pi-methane rearrangement, and the simple skeleton open chain system may undergo to give rise to vinyl cyclopropane. This is a representative example of the 1,4-diene rearrangement going via di-pi-methane rearrangement to give you vinyl cyclopropane. This reaction is highly selective in the sense that when these two double bonds are substituted, means unsymmetrical. So here these two double bonds are just a basic skeleton symmetrical double bond, but when we have these two double bonds are unsymmetrical, here you have a phenyl group here, and these double bonds are substituted by two methyl group, then there is a possibility of formation of two products. So under photolytic condition, this may undergo excitation of pi-pi style excitation to give you 1,2 diradical. We cannot say which of the double bond is exciting to give a diradical, but whether it is exciting this double bond or this double bond, ultimately this 1,2 diradical is going to form 1,4 diradical via the formation of a cyclopropane ring. You can directly go from this structure to this third structure via to give 1,4 diradical through the formation of a cyclopropane ring. And the next is the cleavage of there is a possibility of the cleavage of either this bond or this bond. So if you get a double bond here and then this may cleave to give you this moiety, but is this 1,3 diradical exclusively cleaves this double bond and not this this bond of the cyclopropane and not this cyclopropane to give you this is one of the major product form out of this. So it gives a 1,3 diradical this one and then cyclizes to give you. So when we have unsymmetrical alkene in 1,4-diene where there is a possibility of formation of two products, it exclusively give one product in major amount. So this is the beauty of this rearrangement, and that's why this rearrangement has attracted a lot of attention and several examples of these systems have been tried. The reason for being the exclusive formation is the stability of this 1,3 diradical. We can see here this radical there is a presence of a phenyl group, so there is a possibility of delocalization of this radical in the phenyl ring. For example, we have a phenyl ring here, so this radical can undergo delocalization and hence more stable. This is more stable radical than this, and this is resonance is stabilized by the presence of phenyl group, and hence the more stable radical is not forming double bond across this and hence only the stationary radical, this radical where there is no resonance stabilized substituents present, and hence there is a formation of double bond and cleavage of this cyclopropane ring takes place. So this is here comes the and hence you get this 1,3 diradical and then ultimately to this exclusively this product in major amount. This is not the only example. Several examples have been reported, and in all these cases, all these compounds are the examples of di-pi-methane rearrangement. All these the systems are 1,4-diene separated by 1, 2, 3, 4, 5, 1,4-diene, one double bond between carbon number 1 and 2, a second double bond between carbon number 4 and 5, separated by a methylene group. So whenever you have a system like this, one double bond, a second double bond separated by a methylene group, this is nicely set for di-pi-methane rearrangement, and similarly this one double bond and another double bond separated by a methylene group, and hence this is also nicely set for di-pi-methane rearrangement and may undergo rearrangement to give the vinyl cyclopropane dry product. So all these double bonds in all these examples are unsymmetrical. They are, and hence there is a in all these three cases, there is a 4-5 cases, there is a possibility of formation of two products, but uh, it gives exclusively one product in major amount, and the main reason behind is whenever there is a radical is stabilized by a substituent, there is not formation of the double bond takes place, no formation double bond takes place in that, and hence the cleavage of the other cyclopropane takes place to give the exclusion. Now we'll just look the one by one these examples and see what is the product and why it gives exclusively one as a major product, and then all this. So whenever you have a system like this and people ask you to write the product, you very critically look at the substrate and see the chromophore present in this. You can see that this is a two double bond system, and then one double bond and another double bond separated by a methylene group. And we know that whenever you have it two double bond separated by a methylene group may undergo di-pi-methane rearrangement to give you vinyl cyclopropane ring system. So now in coming next slides, we are going to look at the one by one what is the product in these cases and how it is set for one product only where this. So this is the first example where we have a one double bond and another double bond separated by a methylene group. These two double bonds are unsymmetrical. Here there is a presence of a methyl group. This double bond is there is a presence of a 2-phenyl group, and hence it can undergo it is a 1,4-diene system. It can undergo di-pi-methane rearrangement because basic criteria for di-pi-methane rearrangement is 2 pi bond separated by a methylene group may undergo under photolytic condition it may undergo excitation of one of the double bond followed by cyclopropane ring. So we directly as we have seen in this case, we have gone stepwise excitation of one of the double bond to generate 1,2 diradical, and then the formation of a cyclopropane ring. Here this double bond may also get excited, so we directly go to the cyclopropane ring. In either case, this is the end product. So main intermediate is the 1,3 diradical 1,3 diradical species, 1,4 diradical species via the formation of 1, 2, 3, 4, 1,4 diradical species via the formation of a cyclopropane ring. Now this intermediate is the deciding factor which lead to the major product. Here I have shown both the product A as well as product B, and here out of these two products, one product is formed and other product is not formed, and one out of these two products, one is formed is a major one. And what is the reason behind this formation of the major product lies in this the stability of this radical. We can see here this radical is substituted by 2 phenyl groups, and hence it is highly delocalized. If we can write the delocalized structure, it can be written like this. We can see that this radical is all the way moving from the two benzene rings. So it is highly stable radical as compared to this radical where it is near the substituent of a methyl group, which is no such delocalizing stabilizing substituent present in this. So the radical which is resonance stabilized is not going to form double bond here, and then the cleavage of this ring takes place. So this radical, there is a this 1,4 diradical, there is a possibility of formation of this double bond and opening of this, but unfortunately this route doesn't take place, which may lead to this product, because this radical is resonance stabilized due to the presence of 2 phenyl group. Resonance stabilized, we can write structure like this, and hence this does not form the double bond here, followed by the opening of this. So this doesn't take place, and then the cleavage, formation of double bond takes place here. Cleavage of this cyclopropane ring bond takes place to give you this radical, this 1,3 diradical, which may ultimately lead to the vinyl cyclopropane product one. So this is the major product in this particular case. So here we can see that this is a example of a di-pi-methane rearrangement. 2 double bonds separated by a methylene group. 2 double bonds are unsymmetrical, and hence it can undergo di-pi-methane rearrangement. In di-pi-methane rearrangement, when the 2 double bonds are unsymmetrical, there is a formation of 2 products, A and B, but exclusively one product is formed in major amount, and then basic reason behind is the radical, which is more stable, doesn't form double bond, and hence the other less stable radical forms double bond and lead to the cleavage of this bond of the cyclopropane to give a 1,3 diradical to give this product. Now going to the second example, this is another example of the if you look at this look at this starting material, one double bond and another double bond separated by a methylene group, and hence this material is, this compound is also nicely set for di-pi-methane rearrangement, methane rearrangement under photolytic condition, and this is the basic criteria for di-pi-methane is 2 double bonds separated by methylene group under photolytic condition can give rise to the cyclopropyl drive 1,4 diradical. Now we can see here this radical is resonance stabilized by the presence of phenyl group, and resonance in the previous slide already mentioned the resonance stabilized structure of this radical, and hence the probability of presence of this radical on this particular carbon is less, because all the time it is moving and is more stable. It doesn't form a double bond here, and it doesn't lead to cyclopropane cleavage of this bond. But and what happens, this radical, which is stationary, there is no stabilizing substituent here, forms double bond followed by opening of this cyclopropane ring to give this 1,3 diradical, which once again combine to give a this as the major product. So here also there is a possibility of 2 products, one cyclopropane at this part, or cyclopropane in this part. So exclusively it gives cyclopropane on the, although you can see that this is a highly substituted cyclopropane, and we know that the cyclopropane is highly under ring strain. Although this is a tetra substituted benzene, 2 methyl substituent and 2 phenyl substituent, but still it leads to the formation of product because of the stability of this radical in the presence of due to the presence of phenyl group in this molecule. Going to the next slide example, again this is a, if you very carefully analyze the starting compound, you have a double bond here, you have another double bond here separated by a methylene group. This is once again nicely set for di-pi-methane rearrangement, under photolytic condition. So the first step is the excitation of one of the double bond, either this or this, followed by the cyclopropane ring. So we have directly gone to the cyclopropane formation to a 1,4 diradical species. Again, there is a possibility of two products here. Again, this may lead to the formation of a double bond at this double bond on the cyclohexyl group, and the this is the newly bond form. This is the newly bond form. If we cleave this, you go back to starting material. So in order to go into the product, you have to either cleave this, and again here it is a this radical is stabilized by phenyl group, and also we are cleaving a cyclohexyl group bond, so which is again is not very favorable, and hence exclusively it goes cleavage of this cyclopropane to give a 1,3 diradical via the formation of a double bond here, and this once again combined to give bicyclic system, a bicyclic system. So in the earlier two cases, we have a open chain system. We are going, whenever you have open chain system, we have a monocyclic cyclopropane ring. This is also an open chain system. We are going to get a monocyclic cyclopropane ring, and here we have already double bond is a part of a monocyclic system. So we get a bicyclic system, 3-membered and 5-membered. So this is again, these rearrangements have been found to be very important, very interesting from synthetically point of view, because from an open chain we end up with a monocyclic system, a cyclopropane ring. If the one of the double bond is a part of a ring system, it gives a bicyclic system, and so on and so forth. Going to further second example, here this is again we have to look very carefully the starting compound. You have a one double bond. Of course, it is you have a 3 double bonds. You have another double bond, but these 2 double bonds are only separated by a methylene group. Of course, if you consider these 2, there is no methylene group here. If you consider these 2 also, there is no methylene. But these 2 double bond is separated by a methylene group, and hence these 2 double bonds and a methylene group may participate under photolytic condition to give di-pi-methane rearrangement. And the basic is the steps involved in this rearrangement we have already learned in the previous examples, that it excitation of one of the double bond followed by cyclopropane ring. So this forms these 2 double bonds form a cyclopropane ring, formation of a 1,4 diradical, 1, 2, 3, 4, 1,4 diradical, 1,4 diradical, and then these 1,4 diradical may further undergo cleavage. The cyclopropane ring going to be first formed and then opening up to give a new 1, 2, 3, 1, 3 diradical species. So here whether you cleave, you form a double bond here, or you form a double bond here is a symmetrical, because this radical is again stabilized by this double bond, as well as this radical is again stabilized. So both the radicals are symmetrically stabilized, so you can cleave any one of these. So when we cleave this double bond, form when we form a double bond here and cleave this cyclopropane, this is the newly formed cyclopropane part. So if you cleave this, you go back to starting material. So we cleave this one, and then you have a 1,3 radical and they combine to give this. This is the major product 5 and 3. So you can see already this one of the double bond is a part of a 6-membered ring. At the end of the rearrangement, this rearranged to give you a 5,3 rearrangement as one of the major product in this particular case as well. Going to the next example from the series which we have shown earlier. This is another example of if you critically look into this, so you have to see the basic criteria for a di-pi-methane rearrangement is two double bonds separated by a methylene group. Whenever you have a system like this, may undergo under photolytic condition di-pi-methane rearrangement. And so you have to just see one double bond here, another double bond here, and then separated by a methylene group. So these two double bonds may participate to two double bonds with a methylene group may participate under photolytic condition di-pi-methane rearrangement to give the derived product. If you consider these two double bonds, one of this and another, there is no methylene group in between. So, so this is not set for di-pi-methane rearrangement. Only these two double bonds, separated by methylene group are nicely set for di-pi-methane rearrangement. So first step is the cyclopropane formation with a diradical species. So 1, 2, 3, 4, 1, 4, 1, 4 diradical with the formation of a cyclopropane ring. This is the initial step in the di-pi-methane rearrangement. Excitation of the one double bond followed by formation of cyclopropane, and then again there is a possibility of two products. You can cleave, you form a double bond here and cleave this, or you form a double bond here and cleave this. So there is a possibility of two products here as well. But unfortunately, this this radical is stabilized by a double bond, and whenever there is a stabilization, stabilized radical is not going to form a double bond. That we have already seen, whether it is stabilized by a phenyl group or it is stabilized by the any adjacent double bond. So this radical is stabilized by presence of a double bond. So we can have a structure like this. So and hence there is no such stabilization in this particular radical. So this form a double bond, opening of the cyclopropane ring to give you 1,3 diradical. So this less stabilized radical is formed double bond followed by opening of the cyclopropane ring, and then it combines to give a vinyl cyclopropane as the major product, and other one when there is a stabilization is not going to give the major product. So these are few examples of di-pi-methane rearrangement, where in all these cases there is a possibility of two products, but it exclusively these are all examples we have looked one by one by explaining the steps involved in these rearrangement. In all the cases, all these examples, these double bonds are unsymmetrically substituted, and in all the cases there is a possibility of two products. But the beauty of this rearrangement is that this gives exclusively one reaction. So this is a selective, regioselective reaction, and also another important is that we are going to construct a cyclopropane ring, which is very difficult to construct due to the ring strain. And when we start with the open chain, like in these two examples, in these three examples, we are going to construct a monocyclic system. Whenever there is a double bond is a part of a cyclic system, in this one, we have got a bicyclic system. So this is a really whenever dienes, 1,4-diene undergo very interesting rearrangement to give give this cyclized product, and a lot of attention has been paid by different group of workers to utilize this rearrangement for synthetically important construction of synthetically important product. This is another example of a di-pi-methane rearrangements. This is a very this is a bicyclic system, and this is a common name for this is barreline. This is nothing but it is a 6-membered ring, and there is a another is a, so you have, so one double bond here. So this is a bicyclic system, and we the common name is barreline, but this can be named as a bicyclo 2 cyclooctatrine, bicyclo 2 cyclo, already a cyclo has come, octatrine. So the reason for this is shown here. If you consider what we have learned in the previous slide, that whenever you have a two double bonds, when we have a two double bond separated by a methylene group, it can undergo di-pi-methane rearrangement. So this is, if you look at this molecule very critically, you have one double bond here, another double bond here, and it is again separated by a methylene group. So this ring system is also nicely set for di-pi-methane in all the cases. Whichever two double bonds you consider, either these two or these two, one double bond, another double bond separated by methylene group, one double bond, another double bond, and then again separated by methylene group. So any two double bond are again separated by a methylene group, and hence so this can also set for this ring system barreline or bicyclo 2 cyclooctatrine is set for di-pi-methane rearrangement. And we can see this is already a bicyclic system, and let us see what happens at the end of the product. So we can say that the first step is the excitation of one of the double bond, and then the formation. So we are considering these two double bond, one of these double bond, another double bond, and so, it can give a cyclopropane ring formation with a diradical species. So 1, 2, 3 and 4. 1, 4 diradical with the formation of a cyclopropane ring by considering these two double bond which is separated by a methylene group. Next step is the formation of a double bond and cleavage of the cyclopropane bond. If you either you can form a double bond here, or you can form a double bond here. So if you cleave this, you go back to your starting material. In order to go for the product, if form a double bond here, there is a cleavage of this double bond takes place to give you 1, 2, 3, 1, 3 diradical species, and this diradical once again combined to give you a cyclopropane ring. So this is a cyclopropane ring is formed after the rearrangement, and if you write this structure in a better way, it looks like this: 2, 5 rings and with a 3-membered ring. So this is the product after the rearrangement of di-pi-methane rearrangement of this barreline. Barreline under photolytic condition gives rise to semi-pulverine, is a bicyclic system giving rise to a tricyclic system. A bicyclic system has given 2 5 rings and a 1 3 ring system. So this is again a very good examples of di-pi-methane rearrangement, because we have seen from open chain to give monocyclic cyclopropane. If one double bond is a part of the 6-membered ring, we end up with a bicyclic system, and if a starting material is already a bicyclic, we ended up with a tricyclic system. Common ring is the name for this is semi-bulveline. So again, this is a very interesting product, because we are going to construct a ring stain system, because the construction of ring stain system has attracted a lot of attention, because this ring stain system contains a lot of energy. By any catalytic method, if we can open up, it can release energy and it can be used for energy harvesting processes. This beryllium have already also been exploited for a few more examples, and for like this, if you have a this is a benzoberylene, so one of the double bond is separated by a benzene ring, so it's a benzoberylene, and both the double bonds are connected with a benzene ring, so it's a dibenzoberylene. So now people have just looked what happens in this case. Again, this, if you consider these two double bond, is again set for a methylene group. So also under photolytic condition, this can also undergo di-pi-methane rearrangement, and same as this one, one double bond of the part of the benzene ring, another double bond a part of the this ring system, and separated by methylene also can undergo di-pi-methane rearrangement under photolytic condition. So any two double bonds, either these two separated by these two can also separated by a benzene ring, these two also can is also, so any two double bond you consider is if we consider can also set for di-pi-methane rearrangement, and hence can lead to the interesting. So if you let us see the steps involved in this arrangement, and people have done this, both this this of course this example, as well as people have tried benzoberylene to look at the whether it goes via goes to similar rearrangement or not. And here again, considering these two double bonds and this methylene group under photolytic condition can form a cyclopropane ring. First excitation of double bond and then attack of this to give a 1,4 diradical, 1,4 diradical, and then opening of the cyclopropane ring, formation of the double bond, either this double bond or this double bond. Both can be opened up, because there is no selectivity here, because they both are symmetrical, and hence if you cleave this, you go back to starting material. So in order to see the going towards the product, if you can cleave this, it can give a 1,3 diradical, and then the combination of this to give you a cyclopropane ring. So this is an again this benzoberylene also has undergone di-pi-methane rearrangement to give you benzo semibulvanene, 1,2,5 bond separated by a 3-membered ring, and of course benzene ring is attached as it is. So this people have also tried dibenzoberylene also, considering one of these two double bonds separated by methylene group, all these two double bonds. In all the way, it is nicely set for di-pi-methane rearrangement under photolytic condition, di-pi-methane rearrangement. So considering these two double bond, formation of a cyclopropane ring with a 1,4 diradical, and then opening of the formation of a double bond of one of this, and then the cleavage of this. Here this will be this will be preferred because the aromaticity of the cyclopropane is going to be retained. So that's why this will form the exclusively cleavage of this bond takes place, and then to give 1, 2, 3, 1, 3 diradical, which can once again combine to give a 3-membered ring. So again this give a dibenzo semibulvanene derivative. So this is this work has been exploited by Professor George group from IIT Kanpur initially, and who moved to RL Trivandrum later on and opened a photochemistry research unit. So these are the extension of di-pi-methane rearrangement in the benzoberylene, dibenzoberylene, and of course, so you can see that one 4 diuretic one 4 diene undergo interesting di-pi-methane rearrangement, and when the two double bonds are unsymmetrically substituted where there is a possibility of two products, it exclusively gives one product to and as a major amount the radical which is resonance stabilized doesn't form double bond, whereas the less stabilized radical form double bond, and formation of exclusive formation of the one of the one bond of cyclopropane takes place to give the product. Okay, stop here. Thank you very much.